4.1, number 12. I'm not going to write out the entire verbal description of this problem because it's too much. I'll just say it over and then write down some of the important information from it and hopefully draw a diagram to help solve the problem as I go. So it says that a 5-foot tall person walks toward a wall at a rate of 2 feet per second. Okay. So I'm just going to draw a wall. There we go. And I've got a 5-foot tall person somewhere in here. I'll just put him here. There he is. There's a 5-foot tall person. 5 feet. That's not going to change throughout the whole problem. Right? It says a spotlight is located on the ground 40 feet from the wall. I'll draw a spotlight over here. Beautiful. And it says it's 40 feet from the wall, so therefore this entire distance here is 40 feet. Also, that will not change throughout the problem. We said he was walking at a rate of 2 feet per second. Okay? So I'm going to hold back on that for one moment and try to fill in the rest here. How fast does the height of the person's shadow on the wall change? Yes, there's some sort of shadow on the wall. So the light is shining, I guess, everywhere, I don't know, at him somehow. And then over here, this, I'm going to call it y because it's in the vertical direction. I'm going to define y as the height of the shadow. So therefore dy dt is rate of change of the shadow height. And that is apparently what they want us to find. Okay, so rate of change of shadow height when the person is 10 feet from the wall. So I'm going to go ahead and write that in notation. Find dy dt when person is 10 feet from the wall. Okay, so I need some way to describe when this person of 5 feet stature is 10 feet from wall. So I'm going to label this as x. Okay. Now, that would mean I could write down here when x is 10. So that also means that if he's walking at a rate of 2 feet per second, then I could describe that rate of change as the derivative of x with respect to time. So we also know that dx dt equals 2 feet per second. Now, because that's the rate of change of x here, right? X is changing, his distance from the wall is changing at 2 feet per second. To be as careful as possible, what I should do is write this derivative as negative because the x variable is losing distance, right? He's gaining towards the wall, right? He's getting towards the wall, so that means this distance here is growing smaller. It's getting smaller, so therefore the derivative must be negative. Anytime a variable or a function is decreasing, then that means that the derivative must be negative, so having a negative 2 feet per second here makes the most sense for this situation. Over here, since this 40 value is fixed for the distance between the wall and the spotlight, that means that this initial part over here between the spotlight and the person is always the 40 distance minus how close he is to the wall. So this is always 40 minus x. Nothing can change that throughout the problem. Although x is changing, the relationship between this distance and this distance is always whatever this is, this part must be 40 minus that. All right? We also anticipate that when we finally calculate dy dt, that it will be a negative quantity, right? Because you can sort of tell that as he walks closer to the wall, since his height is fixed, right? As he walks closer to the wall, the fixed height, that the shadow, right, will become smaller and smaller as he gets closer and closer, until eventually, I guess, the shadow would be exactly his height of 5 feet when he was butted against the wall